All right, we are the Wayside Rail team. I'm Michael Hurst.
I'm Gary Gemmel. Karmjot Singh.
I'm Diana Mack.
So I'm going to tell you guys why we're using Wayside Rail, and then Garrett's going to explain some of the existing Wayside technologies. Karmjot's going to talk about the challenges that we're facing on this project, and then Diana's going to talk about our goals and deliverables. So in order for the Superway to be a sustainable solar-powered ATN, we need to figure out a way to get energy from our solar panels and into our bogies, and that's where we come in. We started off by looking at the work that was done last year on Wayside, and we realized that we basically have a fresh start. There's no existing Wayside Rail architecture, so before we spend the entire year working on Wayside, we wanted to make sure that that was the appropriate solution for the problem that we're facing. We started by looking at existing PRTs that are fully functional. On the left here we have the SkyCube system developed by Vectus, and that's running off of a 500-volt DC Wayside Rail in Korea. Another example of that we're all familiar with is the Morgantown system. And on the right we have Ultra in Heathrow, which is 100% battery operated. And another example of that would be the Masdar City installation. After seeing that both Onboard and Wayside have been implemented successfully in the real world, we wanted to dig a little deeper into existing energy supply technologies, both in PRT and in general mass transit systems. The three most common onboard energy supplies are flywheels, supercapacitors, and batteries. So flywheels and supercapacitors are really similar in the way that they both give you high power density. So if you need to make a steep grade or kick on an air conditioning unit inside your cabin, you can do that, but they don't have high energy density. So if you need to go over long distances, they're not the greatest solution. Batteries are sort of the opposite. They give you high energy density, but low power density. So if you're running on a flat grade, you can go longer distances, but they are still limiting. And if you look at the Masdar City installation and Ultra, they both run on really short tracks. And if you take the number of runs that they can do before they need to be recharged and multiply that by the track length, these only run for about 15 miles. And if we're trying to operate a system over a citywide span, it's not the greatest solution. Which brings us to Wayside. And there are two types of Wayside, catenary and rails. So catenary is when you see those cables overhead in a city, and then rails, self-explanatory. Wayside's great. It gives you a constant energy source over long distances. You get good power, but they do have their drawbacks. For catenary systems, the ones that we're familiar with, ground level based ones, you have to put all these cables overhead, and they're really ugly. And some cities that have functioning catenary systems are actually trying to rip them out, not because they're not functioning well, but just because of the aesthetics. And for rail systems, they look a lot nicer. You don't have cables everywhere, but they can be unreliable in areas where you have a lot of rainfall. Anytime you have a live conductor submerged in water, that's not the best situation. And they can also be dangerous, which I have a little video for you guys. So anytime you're building something, whether it's a piece of architecture or a transportation system, there are going to be people that are going to find a way to put their own lives in danger using what you've built. So we always need to be mindful with anything that we're building that we try to make it as safe as we can. And even if you think you've made something that's safe, there was a Superior Court case in Chicago where a man urinated on the live rail of one of their transit systems and got electrocuted. And the Supreme Court awarded him $3 million, which they reduced to $1.5 million because of his negligence. But you never know. And with that, I'm going to hand this over to Garrett so he can tell you a little bit more about existing Wayside Rail technologies.
Alright, cool. So I'm going to talk about the functional specs pretty much of the third rail and a little bit about the fourth rail system. So in the 1880s, Volk, Siemens, Edison, a bunch of guys came up with patents for the third rail design. So this is Edison's. I thought it was pretty cool. It's from 1882. And how it works is I blew up that picture over here. It has a current rail that's usually made out of a highly conductive steel, but it could be made out of like any conductor like aluminum or whatever we need. It's just cost efficient wise for a big job. It's high conductivity steel. Okay, and then so that's the current rail, and then these are the running or support rails. That's pretty much how it works. Oh, so the current will flow through here, through your motor and whatever electrical systems you need to be powering, and then it'll return through one or both of the support rails. Okay, so this is a modern design. This one looks a lot like BART. As you can see, the third rail is on the side here, and it's insulated from the ground, and it also has a protective cover. So yeah, again, we got the two running rails and the third current rail. Okay, and then the collector shoe. The collector shoe is what slides along the current rail and gathers the current. It collects it. So the main thing with the collector shoes, it needs to be in constant contact with the current rail. And yeah, if you don't have that, you're going to lose power. There's fail-safes that we probably should do for that, but that's the main thing. It needs to be in constant contact. BART is a third rail system example. You can see the third rail right there. And okay, so the only drawback that I found is that since we're running current through the support rails or the running rails, that those rails tend to not be grounded as insulated as well as the current rail. So what happens is you'll get some current leakage into the surroundings, and that's what was happening in London's underground railway. They did initial tests with a third rail system, and they were getting, the walls of the tunnels are metal, so they were getting some current leakage there, so they went with the 4 rail system, which for them they did, so this is basically still a third rail, and then this is the added 4th rail, and that's what's returning their current now. So they have this rail at 420 volts, and this one's at negative 110, giving them 630 volts to work with. But yeah, so this rail can be insulated, and it's not, it doesn't have the load of the train on it. All it has is another collector shoe, just like the third rail would have had. Okay, so like Mike said, PRTs that use Wayside Power, Vectis, SkyQ in South Korea, yeah, they're running 500 volts DC. Oh, and I found one of their slides, and they said that they can move their rail around. It's their collector system was variable, is verbatim what they said. So I don't think, I mean, that could mean they're going to do a 4 rail system, or they could do a 4 rail system, but I think that means more like they'll move the third rail around wherever it needs to be. So for us, our track splits. So we're going to have, if we did do a third rail on the big scale, we're going to have a third rail here and there, because once this guy splits off, you know, and he has power over there, we're going to have some splits. Kind of like in this picture it shows it. But yeah. Alright, so last year's research, in this picture they used this is a 12 volt 2 amp transformer plugged into the wall, so 110 volts AC, and that's DC powered. So they used the 12 volt motor and got that working on those 2 rails. So that's pretty basic stuff, and we're hoping to get further than that. But if they would have made one of these rails a support rail and one a third rail, then they would have had a 3 rail system. Okay, some more research that they did is they got that per bogie they're running with 2.4 roughly amps of current. So this year it's probably going to be a little bit different. I know we're adding proximity sensors and things like that, so we're kind of waiting for those results. But a crude analysis of that is if we were to run 10 bogies, which is our goal, on 12 scale, it would be around 25 amps. And I heard Ivan say 30, so we're going to have to work that out. But yeah, and then for the quarter scale, we really don't know. It kind of depends on the motor of what kind of current we're going to be working with. So we're kind of just waiting for those numbers. Okay, so how can we test this initially, at least on the 12 scale? We do have a little PC power supply that's been converted into a power supply, basically, that you can plug whatever you need into it. And it's 12 volt, runs 19 amps, 5 volts runs 30 amps, so that's pretty good to work with. These are our two preliminary designs. We're going to build on these, obviously, but that's a 4-rail system over there. You got one hot rail coming in, a current rail, and then a return current. And then this design is, there's supposed to be like a strip of copper underneath this. It's the switch rail on the 12 scale model, and that would be our hot rail, even though it's just a strip that's insulated from the switch rail. But these are just preliminary designs, so I'm going to pass it on to Kamjot for challenges.
So I'll be talking about the challenges that we'll be facing in our project. So first off, communication between groups is essential. So many of our designs are going to be dependent on other teams' designs, such as the track team, the control team, and the solar team. So it's important that we all work together and not let miscommunication really get us behind. And also if there's changes, the associated groups should know, so they can alter their designs to make it compatible to their modifications. And also safety is another important thing. It's important for any project because you don't want to get hurt and you don't want anybody else to get hurt. And since we're going to be dealing with electricity, we have to take precautions working with electricity and also other human interactions. So for the 12 scale, it's not going to be a big deal because the current is going to be pretty low. It's bearable by humans. But for aesthetic reasons, we're going to be installing some sort of safety cover for the third rail or the fourth rail, as seen in BART and other major rails. And interfacing the bogie with wayside power is going to be another challenge because up until now, the only way the bogies and the parts have been running are electricity or battery packs. So there hasn't been any implementation of wayside power onto the bogie system. So there's going to be some modifications needed to how the bogies are controlled. I mean the power control. So we're going to have to control it to use power from the track. And after we implement electricity to the wayside track, our next step would be to use solar energy to power the tracks and bogie, because the ultimate goal of the Spartan Superway is to use solar energy to power our ATN system. And we plan on hopefully overcoming this challenge this year. Another challenge is going to be fabrication challenge using existing track. So we've been told by the track team that the plan is to extend off the current 112 scale model this year, use a similar design, so that will kind of limit us to how we can create our third rail or the fourth rail, whichever one we decide to go with. And that can lead to fabrication challenges such as the wayside rail. So we plan on using this kind of rail, and if we implement on the top, it's easily bendable along the curves. However, if we put on the sides, it's not bendable, so that can lead to fabrication challenges. And another challenge is control challenge. So the plan is to use 10 bogies to supply current to 10 bogie systems on the track. However, if there's a case that there's only 5 bogies being used, we want to limit the current so that there's not so much current going into the 5 bogies that are running that can cause electrical damage and failure. And with that said, we're putting our 100% best to overcome all the challenges that come. And with that, I'll pass on the presentation to Diana, who will go over the goals and deliverables.
So I will go over the goals and the deliverables, and we'll talk about what goals we want to do this semester and ultimately finish by the end of the year. So the goal for this year is to get a working wayside rail, because last year there hasn't been any wayside rail actually implemented, but there has been tests, as mentioned earlier, tests on wayside rail working. So, and we have to do a lot of research, which has been done past couple of weeks, and we already have 2 designs, either the third rail or the fourth rail design. And One of our other goals is to be able to have to power 10 bogies on the 12th scale and also 3 bogies on the quarter scale. So to do that, we need to be able to figure out how much current that's going to be able to power onto the rail. And then we also need to, which is a challenge because sometimes we're not going to have like 1 or 10 running at the same time, depending on the control scheme. And our other goal is to be able to communicate with everybody. In this picture, we see a guy yelling at somebody. And by a show of hands, who likes to be yelled at to do something? Nobody, right? So, one person. So we don't want to be yelled at, so we need to be able to talk to each other and communicate like verbally and non-verbally. We could do like writing emails, and we already have a blog, and we also communicate like person to person. So it's always good to have like written and verbal communication so that nobody gets confused. And finally, we will have to work together to get all this whole project done. Here's our Gantt chart, and for the most part, the beginning part, we have design, which is we use most of the time researching and figuring out what do we want to use as our wayside rail, either the third rail or fourth rail. And then after the design, we want to be able to build and also like do tests. And then in the next semester, we want to build and implement for the quarter scale and also the 12th scale. So here are our team members' responsibilities. Garrett is our team lead, and he will be in charge of the AutoCAD design. Michael will be in charge of documentations. Kanjat will be in charge of testing and integration. And I will be part of doing the budgeting, and also everybody will be helping each other with like designing with AutoCAD and also fabrication. And there's our references.
Questions?
Okay, so you guys are doing both fourth scale and full scale. So you're doing 2 different designs, full scale and fourth scale.
Probably, yeah. Because the quarter scale is going to be kind of like this cross section, where the third, I mean, that's what I heard from Alex. And whereas that one is totally different. It's going to be different.
No one else has anything. Again, amps by themselves, current by itself is only half of the story. 25 amps at 5 volts won't hurt anybody. 25 amps at 500 volts will kill somebody. So if you're only giving 1/2 of this, you're not giving a power story.
So you want watts?
Watts, or better, is amps and voltage.
Okay.
Because you
I
should
could
be
have told you
presenting
that.
both.
I forgot.
I can tell just from your charts, but be certain about this.
Okay.
The other question I have for you, you chose not to have any energy storage on a system that's connected to solar panels, which is an inherently fluctuating energy source. Do you have a plan for nighttime?
We're planning to have onboard storage, and that's going to be part of the bogey team, not the wayside team. Especially with our 12 scale, we've read that people have had problems where they have sort of intermittent contact, and if you just lose the rail for half a second, then your Arduino is going to reboot and the whole system has issues. So we definitely want some source of backup onboard power, and then the source for the wayside is going to have to store the power from the solar. It's not going to be direct from the panels to the bogey.
One other little bit, you talked about adjusting the current available, or less adjusting the source available. Talk to me sometime about voltage regulation. I think these are constant voltage sources. You guys, I might be able to save you some effort.
Thank you.
So have you measured the power required by these vehicles, current vehicles?
No.
What?
No.
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 Okay.
Haven't even gone over there with a multimeter.
Okay, so
This is all from the past reports.
okay, so that is going to be a huge thing to do.
Also, yeah, we're adding some sensors and whatnot, so everything's gonna need more.
It's going to be different.
So even just from a very simple test, just take the multimeter, turn the motor on, right, go through the multimeter, get the current, what the battery voltage is, the voltage across the motor. You've got a power reading right there. I think it's going to be a lot less than 2 amps. What's that battery voltage? 7 volts?
Yeah, I think it's.
I think it's a lot less for each motor than that. And then the Arduino's not drawing a lot. So I think there's a lot of real measurements that you guys can make that maybe didn't get made yet.
Okay.
All the different teams that are working with electricity, I would like to see a simple black box diagram that shows, okay, over here we have such and such a voltage at the start. Could be the wall for the temporary solution. It could be the voltage you envision, 12,000 volts coming from the utility. If you're looking at the full-scale system outside, not the test track. So you have maybe 3 different conditions, small, medium, and large.
Yeah.
And then for each one, you have a voltage here, and you have a source.
So you want to.
And then you see the next step, which is I take that, and when I get over to here, I'm going to need such and such voltage. And I'd like to see each of those steps, what you label that black box in between a step and another. So for example, you can start with 14 volts DC and drop it down to 5 volts. What is that? Okay, that's a DC to DC converter. So you label that black box DC to DC. You don't explain what's in it, but you just point out that you're starting with such and such voltage, you're coming out with such and such voltage. And if I had a diagram like that that showed each of the major points, the storage system, the source, the motor, whatever each component, the electronics over here, what that's going to be. You mentioned the Arduino needs a power. Okay? So the Arduino is one of those things in that black box. What are you going to give it? How are you going to get it to it? And if I saw that block diagram just sketched out, then I'd have a sense of how you have to step through these various points in the system to get to where you're going. And I think that's an early thing for all those groups that are working with electricity to sort out. Because then what you need to do is go to the other groups and say, okay, we think this is what you're doing. Like you were saying, communicate with the megaphone. Hey guys, is this going to work for you? So that's what I haven't seen yet. And I haven't seen it from the others either, so I'm not just picking on you guys.
We'll get our best man on it.
You're not here.
Cool.
Okay, anything else from this group? All right, thank you very much.
What's wrong?
Should I grab my computer?
Yeah, should we grab ours? Oh, I think that's the problem. Might be the Wi-Fi.
Good example of trying out your stuff before your big presentation to make sure it works.